Well, this is EE 5721, February 14th, 2017. This is our last lecture on the topic of generation. We're going to do 3 sections to this course. We're going to do a generation section, and this is steam, hydro, economic dispatch, unit commitment, hydro, fuel, scheduling. And this is the last lecture in that generation section. Then we're going to do a section on transmission, which will start on 2:16, and then markets, which will start later on in the semester. I'm going to give you homework 5. I'm going to post it tomorrow if I can, 2:15. And I will say right now that we're going to give you till 3:03 to do it. Now, we're going to have an in the building class in Keller Hall 3125 on 228. And that will be a problem session and Q&A about the quiz. And then we're going to have our first midterm exam. Will be the next class period, which will be 3/2/17, which will be Thursday. So this is Tuesday in basically 2 weeks, and this would be Thursday. Will be the midterm exam. I'm going to give you 2 weeks to do this. But I'm also you could say it this way: I'm giving you 1 assignment over 2 weeks, and that gives you time to study. If you've been doing the homework regularly, you should have no trouble doing the exam. Okay, you should have no trouble with studying for the exam, so forth. There's no open book in the exam. I'll bring more things up about the exam. Sometimes I give students a chance to have a formula page, and they go out and get a super fine sharp pencil or pen, and they write down practically the whole chapter. So anyway, so in homework 5, we're going to use a gradient method. Now, a gradient method, I like to use this example. You're going to tune a car, and you can change the timing for the spark plugs. You can adjust the carburetor, and let's say there's one other adjustment someplace, and you start the car up and it's running. And now you go to the timing setting for the spark and you adjust it a little, and it runs a little better. Then you go back to the carburetor and you adjust it, believing that the timing threw off where the carburetor setting was. And then you go and do the third one. And that kind of, you could call it groping or searching, just one variable at a time. Adjust this, adjust that, adjust this, come back to the beginning, adjust. That is a gradient search. Gradient says I'm going to move in the direction of increase. But it doesn't mean that I have to I have to adjust all variables simultaneously. I can adjust them one at a time. And that's very, very common. Given any engineering problem, I have for years, that a group of engineers can find, or they don't have to even be engineers, they can just be people that are smart people and they know they're hardworking. They can find the answer to the problem by this kind of groping, and will probably optimize the problem very, very well. So the pump storage problem is going to use this gradient technique, or just call it an adjustment technique. Pardon me. Here we go. Homework 5 is a gradient method. The pump storage problem is going to use this gradient method. Now, what do we mean by that? Well, what we mean is that we're going to have hours of the day. Let's say 1, 2, 3, 4, 5, 6. We're going to have 6 periods a day in the day, and they're each 4 hours. Okay, all the way over here, 4 hours, and the total adds up to 24 hours. So 1 hour of the day, I'm going to pump. Now that means I got to generate more, so I'm going to pump. And so here's my reservoir, and I've got a pipe that goes down to the plant like this, and so I pump. I put water up. So a different hour of the day over here, here's my load, and then I'm going to reduce that, but I'm going to generate with hydro. Obviously pumping is with it. So I'm going to pump, which adds to the load, and then I'm going to generate with the hydro, which reduces the load seen by the steam. And there are criteria. It's in the chapter. It's in the chapter on pump in that little section on pump storage, and it calls it a lambda gamma. It's the same thing. There's a criteria that says when do you pump and when do you generate. And then when I'm done doing that, I go back and I calculate all the lambdas and everything all over again. And I say, well, it turns out that the next best time to pump is over here. So I'm going to pump over here, pump in the second step, and maybe I generate in the same step the same time step again over here, and then I pump again, and maybe I pump in back in the first step again. Now that wouldn't come up. Let's say I pump here, and then now I'm going to generate in this step over here. So here's generate, and so here's pump. Okay, so the hours that you're selecting, there's a mathematical criteria, and you can see that. And then there's an example that I'm giving you from the second edition of the book, and it's a part of the chapter we left out of the third edition. But it allows you. It's a very intuitive way to see pumping, generating. Now what you do is you pump and you fill this in, and then you generate and you take it back out. So you push it up, the water, and then you take it back. Now you have to take account of the fact that you don't get so many megawatt hours. Instead of using acre feet, we use megawatt hours. I can do that. I can use megawatt hours. I can say water is equivalent to megawatt hours, and it takes so many megawatt hours to fill the reservoir, and then I get a fraction of that megawatt hours out in generation due to the efficiency losses. So that's the first homework problem in homework 5. The second homework problem, when I want to indicate to you that when I started teaching with just the first author of the book, Al Wood, when I started teaching, we used to give this dynamic programming problem, and it was always the hardest problem for the students, and I'm going to see how well you guys do. Dynamic programming. So it here's the way it works, and I'm just going to go through. This is in the book. It's in the lectures. So you've got VJ. This is a time step. RJ is an input here. If we spill J, and the outflow QJ, which is a function of the H of J, which is the hydro megawatts generated. Okay, this is inflow. This is the volume in either megawatt hours or in acre feet. The volume of water that American engineers use is a block of water, if you will, and it's 200 feet by 200 feet. That's an acre by 1 foot. It's called an acre foot, acre feet. Acres are what we use in the United States. You know, if you talk about your house, you can say, well, I have a half an acre lot, I have a third of an acre, that kind of thing. That's typical. But if you have a farm, you might have a 50 acre or a 200 acre farm, or if you live out in Kansas or Texas, you might have a 10,000 acre spread that goes all over the county. Anyway, acres is an area measurement for land, and they just use it the same thing for reservoirs. All right, now we're trying. Let's back up here. We're trying to minimize the sum of the Fi of PS of J, pardon me, which is the steam, and multiply that by NJ. That's the number of hours. That's the number of hours in a time period. So we're gonna divide the period up into n sub j periods. By the way, I wanted to mention we have on the news a dam in California where they're being forced to spill because the reservoir is right up at the top, so the water is coming over like this. One of the dangers of spilling is that it gets into this region and it starts to cavitate, or it cavitates here, and it damages. And you can see this in some of the news footage. It is damaging the front surface of the dam, and there's also an emergency spillway that's not paved. It's not made out of cement, and it's just rocks, and they've been running water through the emergency spillway, and it's eroding. They've got whole chunks of it that are gone. What they're worried about, they're always worried about when you spill, that it's going to come back and undermine the dam, and pretty soon the whole dam breaks. And this thing is a huge facility, and if it breaks, they said a 30-foot wall of water would go rushing through these towns. If you ever saw the movies of the tsunami that hit Thailand back however many years ago that was here, it wasn't too many years ago, of the water coming in from the earthquake under the Indian Ocean, and it just rushed in and it just blew everything out of the way, and people, well, that's what they're afraid of with this spill here, this dam. All right, so we're going to say that we have F, this is the steam of PS is A plus B PS, and there's a J plus C PS of J. That's a J. That simply says our J, the steam, that's cost to generate on the steam. And then the Q for the pH, J, is the hydro. How many acre, in the U.S., this is acre feet per hour. Okay, how many of those big chunks of water per hour? If you live in a country that uses the metric system, it'll be thousands of cubic meters per hour. And so you'll have a completely different set of numbers, nomenclature. Plus GPH plus HPH squared. There we put a quadratic. Now I can tell you that normally the functions normally the function f of PS looks just like, we've seen this. So there's the cost, there's the megawatts coming out here, and this will be cost dollars per hour. Okay. Q is a function that may go pretty much linear and then go up like this. And notice that if this is the change in power to get a certain change in Q, you can say it the other way. What is the change in Q here? The delta Q to get a certain delta P. Now do it over here, and here we get a big change, delta Q, to get a delta P. It takes a lot more water to get each additional megawatt when the curve goes up like this, and that's just basic cavitation and various inefficiencies. Causes inefficiency in the hydro plant. So you don't want to operate up there unless you have to. Now, if you're doing a dynamic programming solution, the key to solve the dynamic programming problem is to say V of j, Vj equals volume in the reservoir end period j is equal to Vj minus 1. Well, Vj minus 1, volume in reservoir end period j minus 1, the previous period. So it says, okay, the volume is equal to the the volume at the end of the previous period, which would of course be the start. Be the start of this period, plus the number of hours for the period Nj times the inflow minus the outflow from the generators minus the spill. And we're not gonna worry too much about spill here. And then we take that equation, and what we want to do is we want to solve it for Q, and it comes out Q of j is the change in volume Now I want you to note that this can be negative. If the volume goes down, well, this term is negative. Well, then how could Q be positive? Q has to be greater than 0. The only way is if this inflow term is very large, and you were using the water that came on this term, plus you were drawing down. So this equation represents the key to solving HydroScheduling problem with dynamic programming. And here we go. We're gonna set this up, and we're gonna say, well, 4,000, 6,000. These are acre feet. Let's say 8,000, 10,000, and 12,000. Acre feet of water. Just AF. And I'm going to make these into a state. And here's my time periods down here. 1, 2, 3. So this is N nj equals 1, and nj equals 3, and this is 4, etc. So, at the beginning of each time period, I'm going to have a state of the reservoir. And let's say it starts out at 6, and it just goes level. Okay? It does not change volume. Well, if you go back to the equation then, it says, well, let's see, Q equals Vj minus 1 over Nj plus Rj. Well, that means that this is equal to 0. And there's no change. The volume J and J minus 1 are the same, so Q equals R. Simply said, whatever inflow, that's the outflow from the hydro plant. Now suppose that I let the reservoir go up. And let's do this, let's put this in red here. This one says Q equals Vj minus 1 over Nj plus R. And let's see, the J minus 1 was 6,000. And this is 8,000, so this has got a net on the top of 2,000 plus the R coming in. And so it's filling, it's going up. The reservoir is going up, and that means that Q is smaller. Q is a Did I do this wrong? No, it's going up. Q is smaller. Somebody should correct me here. I have this equation wrong, people. I have this equation wrong. The equation should be Vj minus 1 minus Vj over N plus R equals Q. Yeah. So that this equation should be Q equals Vj minus 1 minus Vj over N plus R. Well, this still equals 0, so this didn't stay the same. Now here, in red, it should have been Q equals 6,000 minus 8,000 over N, which is minus 2,000. And that means that I'm using I'm using the R, and I'm using I have a negative number here, and so Q is much smaller. Q has to be smaller, assuming that R is larger than that 2,000 over N, and it's 4 hours, so that's 500. Let's say R is 1,000. So Q is much smaller, okay? Q is much smaller. So if we said up here, let R equal 1,000. Well, then this one here is just 1,000. So Q equals R. So Q equals 1,000 acre-feet per hour. But up here, I have minus 2,000 over N, which is 4, plus 1,000. Minus 2,000 over 4, so that's minus 500. So now Q is only equal to 500. See, Q goes down. So Q gets less if I'm letting the reservoir fill. And down here in green, I will do this. And this one is Q equals what? It's 6,000 minus 4,000 over N plus 1,000. Well, that's 2,000 over N. So that divided by 4, that's 500 again, but now it's plus, it's 1500. Q equals 1500. So if I'm drawing the volume down, then I'm running the hydro plant stronger. So the generation goes up as I pull it down. And as I just let it level, it drops to 1,000. If I let it go up, it's equal. And eventually, I can't let it go up anymore. I just don't have enough infill. So, we're going to do this HydroScheduling problem in the same manner that we did watching that problem with finding the cheapest route across the United States. I have these steps: 4,000, 6,000, 8,000, 10,000, 12,000. And I have the same steps at the end of the periods. Oh, a bunch of dots. We call these states, and here's period 1, period 2, period 3, etc. Now, what I want you to look at is, if we start out, I would like to find the optimum path. Well, maybe the optimum path is to let, maybe a path is to let it fill up to 8,000, keep it level, and then all the way down to 4,000. That's a path over to this point. Well, there might be a different path to get to that point where I do this. I level it, and then I run it up like this, and then I run it all the way down there. And either one of those represents a path. And they each have a cost, because every time I calculate the path, I know that I get a certain value of Q. Well, if I have Q, from Q I can get pH. I've got the reverse function that says given Q, I can tell you what pH is. And then the steam is simply equal to the load minus pH. So I subtract pH from the load, that's the and then I know PS, and then I take F of PS, I plug that into PS, and that gives me the cost. That gives me this cost to go from here to here during hour 1. And hour 1 sets the... Similarly, this has a cost. And depending, and I can have multiple paths. Let's say up to this point here, I could have taken a path that went here and then went up here. Now notice that I've got two different ways to get there. There will be a cost to go this path up and over. There will be a cost to get to this path. So therefore I have to calculate the minimum cost and record it and remember which one of these was the path that gave me that minimum cost. Just exactly the same that we did for the dynamic programming solution of the traveling salesman across the country, looking at the cost of the various toll roads as we put it in that problem. Now, the thing that we want to worry about now is, so for a DP solution, you can get a quote better solution by making it smaller volume steps. Oop. So instead of 12, 10, 8, 6, 4, I could go 12, 11, let's forget the zeros, 9, 8, 7, 6, 5, 4. I doubled the number of points. Or I could go 12, 11.5, 11, 10.5, 10. So I can make it much more granular. But more states means that the dynamic program is going to take a lot longer. It's going to take a lot longer. So once again, the summary of DP for a HydroScheduling is as follows. Q. Now this Q is equal to V, and it's J minus 1 minus Vj. On the WebEx, I had this reversed, plus Rj, and that gives me Q. So I know where I'm going, what the dots are. I divide by N, I add the R, I get Q. When I have Q, I get pH. PS equals P load minus pH. And from there, I get F of PS, and that's the cost of the path. Okay, so that's the way this thing goes. And you calculate the cost of each path, entering a point, and you take the minimum one, and you remember which path that was. You remember what the total cost to get to that point, and then you go on to the next stage, the next set of the next time period. So in the problem that you're going to be given, there's a special difficulty in that. Let's see, 6. In the homework that you're going to be given, let's see, 5. It's going to have a plant the Q of H of pH versus pH, and then it's going to go like this, and this is begins to get less and less efficient, actually because of the head effect. So here's our reservoir. Here's the penstock, and the higher the head that the water falls through, that's this head here. Now just drew some arrows like this. The higher that head, the more water you get. So as the reservoir gets lower, you get less power for the same amount of water because it's not falling through. It's the loss of potential energy is less as you're falling through. Problems with dynamic programming. Now, as I said, I would use LP today, but dynamic programming was applied many times. I worked at a company that did a large HydroScheduling program for a utility in Spain, and they had many situations like this: reservoir with a dam, running down the river, another reservoir and another dam, and running down the river and another reservoir and another dam. And sometimes you had other rivers coming over where you had another river flowing like this and coming in here, and I had reservoirs on that one too, and then I had another one up further. So this one would come in here, this one would come, and they'd all send water down like this, and so you had a network of rivers, hundreds of not hundreds, let's say 30 to 50 different power plants, all networked together on a network of rivers. So that meant that they could get a lot of use of the water, and we wrote a HydroScheduling program for them. Well, here's the problem when you have this. Just show you with 2. V1, V2. So I could solve this with a relaxation technique. So here's all the V1 volume states, and I do a DP, and I just hold V2 constant, and I do an optimum path, and then I say, okay, now hold this one constant, and we'll do this one. And so now I've got these states, and the input has got a schedule coming out of this guy. So now I do an optimum path for this one. Then I go back and do this one while I'm holding this one, and I go back and forth. That process converges very slowly, if at all. So it's not a good technique for these coupled hydro plants. And what they had to do, the fellow that I worked with came up with the following technique. He said, well, we're going to have let's say we're going to have two volumes here, V1 and V2. And so we're going to have V1 and V2. And so we're going to, let's say, 12,000. And this is, let's say this is 12,000. And this is 10 and 8. We're just going to use three steps. 12, 12. And then I'm going to go back to 12 here, but this guy's going to go down to 10. So now it's 10 and 10 and 8. And this is still 10. And now I'm going to go 12, 8, 10, 8, and 8, and 8. So I've got 9 combinations. You see, you can see it here. I've got all possible combinations where I have 3 volume steps for each facility. So I have all 9. And now these become the volume states. Well, you can't do that with 10 reservoirs down the river, because 10 times 10 times 10, it gets to be an enormous number. But what they did do is they said, look, the difficulty is when I have 2 of them, so that I would then schedule by pairs, and I would find a best schedule for these 2 while everybody else is the same. And if I had a system like this with a hydro facility going down the river, I would schedule these 2, and then I would come back and I would schedule these 2. Okay, so I'd schedule, let's say 1, 2, 3. I would schedule 1 and 2, and 3 is constant. And then I would schedule 1 constant, and I would do 2 and 3. Okay, and that allowed the changes to work their way through the system. The interesting story that I like to tell, the happy ending, was that they started this out with a fairly inadequate computer, and so the HydroScheduling took a long time, and they couldn't do very many cases, and they weren't too happy with it. But it was working, and they liked the results, but they wanted to do more exploring. So they bought a special computer just to run the HydroScheduling, and it saved them lots of money. Again, when you're working on these power system problems, if you can save a small % of the annual fuel budget, you can buy an awful lot of computers and buildings and personnel. And maybe you get yourself a big raise. Nah, we can wish. Anyway, you can save a lot of money for the company. The other thing that I'm going to talk about is my student. I had a student do a problem with linear programming, and I wanted to show you some of the results, assuming that I can find them. There they are. I challenged the students several years ago in the course to do a problem, and so I wanted them to do it with LP. And so it had 3 generating units. Each one had had a cost curve like this, and he put them into 3 points, 3 linear segments. Well, we've already had a homework problem that did that. And he solved three generators simultaneously like that, and then it had a load profile that went 1200 all the way up to 2000, back to 1800, back to 1000, down to 800, and down to 600. So that's 6 periods of 4 hours each, 24 hours. There's 24 hours. 6 periods of 4 hours each. And he did this. He had 2 identical hydro units, although they started out with different water, V1 and V2. So he had this problem of doing it this way, and he built it with his linear program with MATLAB. Each of these had 1,000 acre-feet per hour input like this, and he solved it, and the results I thought were very interesting, and I will show you here. This is the steam plants, and the clear one is P3, the dark is P2. These are actually colors, and that's the way they print in black and white. And this is P1. Well, the steam is running the greatest during the first 3 hours, especially these 2 hours. But it's not too different, and then it levels off. Here's the hydro plants. The dark one is Hydro 2, the lighter one is Hydro 1, and he runs more from Hydro 2, and we're going to see this on the next page. He shows us the water level in the 2 plants. So here's V1 on the top, reservoir 1, and here's reservoir 2. And reservoir 1 starts out and comes down, and then it just lets itself fill. V1 doesn't do much after this 3rd hour. And V2 goes all the way down and stays there and runs the plant. It doesn't allow it to fill except a very little bit at the end. And so this gave him the optimum schedule. But he didn't have to do any tricks of trying to come up with combinations of hours and so forth, like you would with dynamic programming. I will say, there's a topic that we did not cover, and that's called production costs or costing. And there's a product. I'm going to put the product advertisement here. ProMod. Now, it's not the only one on the market. I just don't know the other ones very well. ProMod is so famous, and it's been around for as long as from the 1970s. But ProMod is a program where you can say, all right, we're gonna simulate our power system for the next 20 years, and we're going to show different construction schedules of new power plants. Should we build one big power plant that's going to take 12 years to build, or should we build 2 smaller power plants that are a little bit less efficient, but they're each going to take 5 years to build? What's the cost difference, if any? The ProMod will just do, that's what it's for. And you can put hydro schedules into ProMod, and it'll do an optimal hydro schedule at the same time. It'll simulate anything like that. I was telling people before that ProMod, if you ever get into an opportunity to become the company ProMod expert, do it. Because if you become a ProMod expert in your company, other companies will come and try to recruit you. They will pay you more. ProMod experts are few and far between, and I have to say this, and this is a product of ABB, although ProMod has gone through an ownership path that's unbelievable. It's a very hard program to learn. It's a very hard program to use. We had a copy for a year, and we had to call the expert in over and over to teach us, how on earth do you set this thing up? How on earth do you use it? How do you run it? They don't give you a user manual. There is no user manual. You have to learn it through classrooms and by hands-on. It's an incredible thing. I think that's one of the real poor aspects of ProMod, is that it is so complicated. But they don't have a written manual, user manual. You want to know how to put the data in? Get somebody to tell you. There's no manual. You can go and say, here's the files. Here's the protocol for the files. Anyway, that's a program that can do HydroScheduling. So if you ever get into a place where you have to do some HydroScheduling, you could try to get ProMod, but I have the other thing. Not only is it very complicated, it's very expensive. Very expensive, and you don't want your boss may not go along with buying ProMod for your group. You're going to have to do your own code. You'll just have to do your own code. Okay.